All right, hello, my name is Sage Weil. Today I'm going to give an introduction to Ceph, the open source distributed storage system. I'm going to start by talking a bit about what Ceph is and why we care about it, why it's important. I'll do a bit of a deep dive into the Ceph architecture, why it's built the way it is, how it works, what are the core concepts, what makes it different from other systems. Focusing mostly on RADOS, the underlying storage layer, but also talking about the object, block, and file components that are built on top of it. Then we'll shift gears a little bit and talk about how Ceph is managed and some of the user-facing features that make it easy to consume. And finally, we'll talk a bit about the open source community and software ecosystem. So what is Ceph? It's been described as software-defined storage, as a unified storage system, scalable distributed storage. We branded Ceph as the future of storage. It's on a lot of our t-shirts. And people have also described Ceph as the Linux of storage. But all these phrases mean slightly different things to different people. So to try to get to the crux of it, I think the first thing to recognize is that Ceph is open source software, emphasis on a software that can run on any commodity hardware. So commodity servers from any vendor. It uses typical standard IP-based networks, and we can use all the usual standard types of storage devices, hard disks, SSDs, NVMEs, NVDIMMs, and so on. And finally, it's important to recognize that Ceph is a unified system in that you can serve object, block, and file workloads from the same cluster, from the same hardware, using the same software stack. So Ceph is free and open source software. That means you have the freedom to download and use Ceph. It's free in that sense. You also have access to the source code. It's open source, so you can introspect, look at how the system works. You can modify it. You can share your changes as long as you conform to the open source software license. This gives you freedom from vendor lock-in. You can choose from many different companies and organizations that are building products and services based on Ceph. And if you don't like them, you can switch to somebody else without having to, throw out your software stack. And by virtue of the community, you also have the freedom to innovate in the space by integrating Ceph with other software systems and adapting it to your particular use cases and workloads. Ceph is designed and built to be reliable. Our goal is to create a reliable storage service out of inherently unreliable components. So the architecture is designed with no single points of failure. It provides data durability via either replication or erasure coding of your data. And it's designed to be continuously available so that you have no interruption of service from rolling upgrades, expansion of your cluster, contraction failures, and so on. And it's also reliable in the sense that we, as a rule, favor consistency of the system over correctness over performance. So we're more concerned with making sure that when you read data, it's the exact same data that you wrote, and we'll avoid taking shortcuts in order to make things go quickly. Finally, Ceph is scalable. We describe it as an elastic storage infrastructure. That means that your storage cluster may grow or shrink over time as the size of your data sets or your workloads or your overall requirements of the organization change over time. You can add and remove hardware from the system while it's online and under load, both to deal with failure and hardware refresh, and also to expand capacity or deploy new different performance classes or whatever it is. And we can scale in a number of different ways. So you can scale up by simply using faster, bigger servers and storage devices. You can scale out by adding additional nodes or racks of nodes and more storage devices to get more capacity and performance in the system. And you can also federate multiple clusters across multiple sites using a set of asynchronous replication features for disaster recovery type use cases and to provide availability in the event of an entire data center site outage. And finally, we describe Ceph as a unified storage system. So that means we provide object, block, and file service from the same software, from the same cluster. And all of that is built on this underlying component that we call RADOS. RADOS is the sort of reliable, elastic, distributed storage layer that makes sure that data is replicated and handles all the hardware details, handles data placement, migration, rebalancing when you add and remove hardware, all of that to provide sort of this underlying, reliable, and highly available storage layer. And then on top of that, we have different components to provide different types of APIs. So RGW, the RADOS gateway, provides an S3 compatible and Swift compatible object storage API, buckets, using a RESTful get and put type interface. RBD, the RADOS block device, provides a virtual block device interface. This is used very widely in public and private cloud deployments and platforms. So virtual disks usually backing virtual machines. And CEPHFS is a distributed network POSIX file system that allows lots of clients to have a shared access to a single file system namespace with your usual POSIX-like semantics. So in this talk, I'm going to do sort of a deep dive into how this architecture is put together and how it works, starting with RADOS, this underlying layer, and then moving on to RADOS Gateway, RADOS Block Device, and the Ceph file system. So let's start with RADOS. RADOS stands for Reliable Autonomic Distributed Object Store. This is the common storage layer that underpins all the other services in Ceph, and it provides this low-level data object storage service that's reliable and highly available, that's scalable, both when your cluster is initially deployed on day one, be sort of arbitrarily large, and also on 1, 2, 3 years down the line, when you are refreshing hardware and expanding and deploying more storage and so on, it's also scalable sort of after the fact. And RADOS's job is to manage all the replication and erasure coding of the data in the system, figure out where that data should be stored on what nodes and what storage devices, rebalancing, scrubbing for integrity checks, repair. All of that stuff is handled by this underlying RADOS storage layer. It's designed to provide a strong level of consistency. So for those familiar with the CAP theorem, RADOS is a CP system, not an AP system. And its purpose within a larger Ceph architecture is to simplify the design and implementation of the higher layers so that the file, block, and object components can focus on the complexities and intricacies around providing that particular type of API, while RADOS can handle the safety and availability of the data. So Ceph and RADOS is a software system, so it's comprised of a number of different storage daemons. The first one is the monitor, the Ceph monitor. These monitors are a central authority for authentication, excuse me, for authentication, data placement, and policy in the system. They're sort of the central coordination point that manages all the other daemons that participate in the system. They protect critical cluster state with an algorithm called Paxos. And they're typically somewhere between 3 and 7 of these per cluster, usually spread across different hosts or different racks so that you have reliability and availability. There's also a Ceph manager daemon that has 2 roles. The first is to aggregate real-time metrics about all the daemons that are participating in the system, things like what's the current level of throughput, what's the current disk utilization, what are the various internal metrics that all these other software components are reporting. Aggregate all that so you have a real-time view of what's happening in Ceph. And the second job is to provide a host for pluggable management functions, things like the dashboard for user management or automated background tasks that are doing optimization and other automated functions. These can all be implemented as Python modules and are hosted inside the Ceph manager daemon. There's typically only one, or always actually only one active manager daemon per cluster, but you usually will have a number of standbys so that if the first one fails or the host that it's running on fails, another one can take over. And finally, we have the Ceph OSD, the object storage daemons. These are the workhorses of a Ceph cluster, and their job is to store data on a directly attached hard disk or SSD and to service I/O requests to that data. But these OSDs are also smart. They're not just a passive storage daemon, but they cooperatively communicate with their peer OSDs, and they work together to make sure that data is safely replicated and consistent to make sure that things are scrubbed and rebalanced, and that everything is A-OK. There can be a small number of these. It's a very small cluster, 1 or 3 of them. That's sort of a proof of concept type deployment, or many, many thousands of these in a larger cluster with tens of petabytes of data. Now, one of the goals of the Ceph architecture is to avoid sort of the problems with legacy client-server type architectures. So in past decades, client-server architecture served us well, but as the services scale out, it becomes very difficult for systems to maintain the illusion of being a single server when in fact they are hundreds or even thousands of individual servers. And so there are a number of tricks that systems have used to sort of maintain this illusion, things like virtual IPs and failover pairs and gateway nodes that sort of hide the layout of data on the back end. But all of these design methods are limiting and overall sort of limit the design of the system and limit the overall performance and consistency and behavior. So instead, CEPH is designed around what we call a client cluster architecture, which basically means that there's an intelligent client library that's sitting at the application side that understands that it's not talking to a single server, but is in fact talking to a cluster of cooperating servers and can do intelligent things like smart request routing, making sure that IO requests are routed to the correct node that has the actual data in question. This allows us to do things like flexibly address all the nodes, all the daemons in the system. Manage the fact that data might be moving around in the background and provide sort of a seamless experience for the application. And at the end of the day, we're providing the same application API. As far as the application is concerned, it's writing a data object into some logical construct. And it's this library that's handling sort of the internal details of where exactly that request should be routed. So one of the first questions when building a system like this is, where should you store your data and how do you know where you put it? So if you imagine an application that wants to read or write a data object, it needs to know where to put it. So a sort of a naive approach would be to have a metadata server that has a big table of all the data objects and what servers, what nodes they're stored on. The problem with this is that it involves a separate lookup step. If you're trying to read an object, you have to find out where the object is first and then go and contact that particular node. That's slow. And it's also hard to scale that metadata service to trillions of objects when you're storing many, many petabytes of data. So what many other distributed systems, and Ceph as well, do is something called calculated placement. So the idea here is that when the library starts up, you get this initial map, a concise description of the structure of the cluster, what servers exist, and how data is supposed to be laid out across them. And then whenever you want to read or write a particular data object, you do some calculation. That's a function of the state of the cluster and the name of the object, and that spits out the location in the system where that data should be stored. And then you can contact the appropriate node or daemon in the system. And then if some time goes by, maybe the cluster gets expanded, a node fails and data gets moved around, the application can get an updated version of the topology of the cluster. And so later on, when it needs to go read back that data that it previously wrote, it can repeat that calculation. It might get a different answer this time, and it'll go and contact the appropriate node where that data should be stored. This avoids the complexity of having that overall lookup table and tends to scale very well when your clusters are very, very large. But this brings up the question of what these data objects actually are. So this is sort of the fundamental underlying unit of storage in RADOS is an object. So each object has a name. It's identified by a unique set of characters, usually 10 characters that have some semantic meaning, presumably. Each object can have some attributes associated with them. These are sort of analogous to extended attributes in a file system. You may or may not need to use them, but you can have some sort of lightweight metadata associated with that object. But the bulk of the data of the object is really in the byte data or key value data. So the first type of object looks kind of like a file. You can store a bunch of bytes in it. Typically, objects can be, a few bytes up to maybe tens of megabytes. On average, and by default, most objects and stuff are around 4 megs, but it can be sort of anything within that general range of sizes. RADOS also supports a type of object called OMAP objects that can store key value data instead of byte data. And so the idea there is that the content of the object is actually a map of some number of keys to some number of values, similar to sort of a flat database, NoSQL type lookup table. And any object in RADOS can contain either byte data or key value data, or actually both, although in practice it's usually one or the other. And then sort of stepping back a bit, all of these objects exist within sort of a logical grouping called a pool. So pools usually map to some sort of use case for deployment. So you might have a pool that contains all the virtual machine images for your cloud hosting infrastructure. You might have another pool that contains all the data for a file system, that sort of thing. So it's sort of a high level, large grouping of objects in the system. So the question is, how do we how do we decide where these objects should be stored across the hundreds, thousands, or tens of thousands of OSDs in the cluster? So if you imagine you're storing all kinds of different data in Ceph, right? It might be disk images, files, video files, pictures. Let's assume for as an example that we're storing a big MPEG video. So the first thing we would do is break that large video, maybe it's several terabytes, into lots and lots of RADOS objects. So a long sequence of 4 meg objects, say, and they're all going to have names that are, probably end with a number or something, because it's sort of this sequence of objects. And then, of course, all of these objects exist within a pool. So we're dumping all this video data into a single RADOS pool. And so when you do this with lots and lots of videos, you end up with a pool that has bazillions of objects, millions, billions, trillions. It sort of depends on how many terabytes or petabytes of data you're storing in the system. But it's a effectively unbounded number of objects exist in this pool. And so we have to decide where all these objects should be stored in the system. So the next step that Ceph takes is to break this pool down into a number of different fragments or pieces or shards that we call placement groups. And it does this by taking a hash of the name of the object and then using something like a modulo operator to map them to one of the, say, 4096 in this particular example, different placement groups that are comprising this pool, so that each placement group has, some fraction of the total objects of the pool, and those objects map into placement groups in a deterministic way. And finally, for each of those placement groups, each of these sort of fragments of the overall data set, we have to store it on multiple devices for redundancy. So in a 3x replication type scenario, then each of these placement groups would be sort of pseudo-randomly assigned to 3 different OSDs in the system. But these are small. We have a lot more placement groups than we have OSDs. So if you sort of look at this from the other perspective, if you consider one single storage device, it's actually going to store, tens or maybe around 100 different placement groups that might be all from the same pool or might be different pools or whatever. So each OSD storing lots of different chunks of the overall data set, overall pools, placement groups that are stored within the Ceph cluster. So you might be asking, why do we have this sort of intermediate stage of placement groups? Why don't we just sort of assign objects to storage devices? And there are a couple of reasons for this, but it's helpful to look at what the alternative design options might be in this case. So in sort of the simplest approach, you could simply choose to replicate disks in your system, right? You could take all of your disks, they're doing 3-way replication, so you have a bunch of sets of 3 disks, and these disks are simply all replicating the same identical content. So sort of a RAID 0 or RAID 1 type configuration. The first limitation you notice is that in order to do this, all these disks have to be exactly the same size, or at least you can only use sort of the smallest size of the 3 disks. So that's a bit of a limitation, but maybe you can get past that. If you instead replicate placement groups, for example, though, things are a bit better because you have each individual placement group, so you can sort of randomly choose which devices it's assigned to, and they're sort of spread around. You can have different size devices because the smaller devices might just have fewer placement groups than the larger devices. But it's a bit more flexible in that sense. And finally, you can imagine taking this to an extreme where you take every single object in the system and you sort of randomly map it to different devices. And you end up with a situation where sort of every set of OSDs or disks in the system is sort of sharing replica data with every other disk. So you have sort of a tightly, fully connected mesh of storage devices. So let's look at what happens when a disk fails. So in the disk replication scenario, if a disk fails, the first thing you notice is that you have to have a spare device that's empty and totally unused in order to do a repair. And then also that spare has to be sort of the appropriate size so that you can make a new copy of the failed data onto a new disk to compensate for the fact that you lost one. So this is a couple of problems. First, you have to have these spares around. They have to be the right sizes. And before the failure, you have an idle disk that's not being used, so you're essentially wasting that resource. And the second thing is that the recovery process is bottlenecked by the throughput of a single disk. So you can only recover as quickly as this replacement disk can write its data, or the source can read its data. And as we know, hard disks are getting bigger faster than they're getting faster, which means that the recovery time for a single disk is getting longer and longer, which means that you have a wider window of vulnerability during which sort of the durability and replication count of that data is somewhat compromised. So that can be problematic. In the case of placement groups, it's a little bit better. because you notice that when we lose a disk, we have copies of the lost placement groups on lots of different devices. And we can choose new location for those placement groups that are independent and also pseudo-random, so that this cream-colored one can replicate to one node, and the blue one can replicate to a different node. And so you suddenly have a parallel recovery process. So both of these pieces are recovering in parallel. It'll happen twice as fast. In the extreme, you can imagine if there were 100 placement groups on that failed disk, it could go 100 different disks recovering in parallel, taking 1/100th of the time. And also, you'll notice that we didn't need a spare, because we can simply move these placement groups to the remaining sort of empty space on the surviving nodes in the cluster. So that means that all of our hardware is being utilized at all times. We don't have this sort of waste of having sort of idle disks sitting around. And finally, if you look at sort of the extreme case where we're replicating every object, if you fail a disk or if you lose a disk, then the data on that disk is replicated a little bits of it on every other disk in the system. So you have sort of this all-to-all probably recovery process where they're all copying data around all over the place, which in theory is possible, although there are probably some practical considerations around how do you actually keep track of where all these objects are and should be stored, and how individually, if you consider them, it's probably more overhead to figure out exactly where they should go. But if you ignore all that, in theory, it should work. The larger problem with that scenario or with that strategy comes when you think about what happens when you have a concurrent failure. So if you imagine that you're very unlucky and not just one device failed, but 3 devices failed at the same time, what happens? So in the original scenario where you have these sort of replica sets of 3, it's most likely that if 3 devices fail, they're not all going to be from the same replica set. They're going to be spread across different replica sets. And so you're never going to lose, or very rarely are you going to lose, all 3 replicas of the same data and actually have data loss. Usually it's going to be spread across different replica sets and you'll be able to recover. So very few triple failures cause data loss. On the other hand, though, if you think about the scenario where we were replicating individual objects, because we have a bazillion different objects and they're all randomly placed, pretty much every set of 3 devices within this cluster has some data that is replicated on those, just on those 3 nodes, which means that there's pretty much always going to be some data loss. It might not be very much, but you're always going to lose some data. And that can be particularly problematic when sort of the integrity of an overall data set depends on having all the data and not sort of having some random subset of it disappearing and hoping that the rest of it will still hang together. So that's very concerning. And then if you look at placement groups, then it's sort of somewhere in between, right? So some triple failures, most triple failures probably won't take out all 3 replicas of a placement group, but some of them will, more so than in sort of the replica set, where you essentially just had 1 placement group per device. But it turns out that the sort of placement group strategy is a balance of these competing extremes. So in the academic literature, this is described as declustered replica placement. And it's this basic trade-off. So if you have more clusters, more placement groups, then you have faster recovery and a more even data distribution. And if you have fewer clusters, if you have fewer placement groups, then you have a lower risk of concurrent failures leading to a data loss event. And using this strategy with placement groups is a happy medium because you can avoid those spare devices, and you can adjust by adjusting the number of placement groups. You can sort of choose where you want to be on that spectrum. Neither extreme is the perfect world, but you can sort of have this balance in durability in the case of concurrent failures and the recovery time that you want to tolerate. And when you do that, then sort of having a complete strategy to keep your data safe is really then around avoiding those concurrent failures in the first place, or ensuring that when concurrent failures do happen, they don't lead to data loss. And the way to do this is to separate your replicas of your data across failure domains. So for example, you might have a cluster that's comprised of hosts organized into racks into rows into data centers, and so forth. You might want to separate all of your replicas across racks so that when you lose an entire host, which might have 24 disks, none of those disks are going to contain multiple replicas of the same data. Your replicas are always separated across racks. And so the way Ceph does this is it creates a hierarchy of the source devices of the system that the cluster understands, how all these devices are organized. That should be aligned to the physical infrastructure as much as possible. And then allows you to express the placement policy in the system in terms of that hierarchy. So again, you might say that I want 3 replicas all in separate racks. And that means that, if I lose a top of rack switch, I only lose 1 replica of anything, because replicas are always spread across racks. Or even if somebody's walking down the data center with a cart and they sort of veer off to the side and crash into a rack, or the cooling fails or something, and you take out a whole bunch of servers due to some correlated event, by having that infrastructure aligned to sort of the physical placement of those devices in space, then you try to correlate those failures with the failure domain, and minimize the risk that you'll have disks simultaneously failing that are in different racks that might be sharing the same data. And so the challenge then, the real question is, how does Crush do this? How do we have this magic policy that places all these bazillions of placement groups across devices, that respects this desire to have replicas separated across failure domains and so on, do all the things that you want to do in a real storage system? And the answer is with an algorithm that we call Crush. So Crush is a pseudo-random placement algorithm. It's a repeatable deterministic calculation function of the state of the cluster and the name of the object that spits out where the data should be stored. So the inputs are the topology of the system, so that hierarchy that I was talking about, how OSDs are organized into hosts and racks and rows and so on. The pool parameters, like the replication factory and my placement policy, and then the identifier for the placement group that I'm actually going to store. And you put all that into Crush, it does some calculation, and it spits out a number. That's essentially not a number, but an order list of which OSDs that placement group should be stored on. And then that's where you go and you put your data. And so as part of these pool parameters, Crush allows you to write rule-based policies that describe how those replicas should be placed. So you can do things like say, I want 3 replicas in different racks. Maybe I only want to use SSD devices. That's one of the inputs to the function, and spits out which devices to use at the end. You can have something more complicated, like if you're using a erasure-coded scheme, that's 6 plus 2, so you have 8 sort of shards of your data. Maybe I want to have 2 of those shards per rack, so spread across 4 racks. But of those 2 shards that are within a particular rack, I want those to be separated across different hosts. And I only want to use hard disks. Something like that is also possible. So one of the key properties of Crush is that it generates what we call a stable mapping. So that means that if you have a particular state of the cluster with some set of devices and there's some topology change, like a node is added or a device fails or something like that, then we want the amount of data that has to move in order to rebalance the distribution to be proportional to the size of the change made. So for example, if I have 100 nodes and 1 node fails, then roughly 1% of the data is going to move. So when I repeat my Crush calculation with all the existing placement groups and find out where they should be stored now, given the new state of the system, about 1% of those placement groups will be mapped to different OSDs and will require some sort of data movement. So that's a very important property with storage in particular, because moving data around is very expensive. And finally, Crush supports varying device sizes. So every device in this hierarchy has a weight, and that weight determines the sort of proportional amount of data that will be stored there, so the number of placement groups. So you can have hard disks, SSDs of completely different sizes in the system, and if you weight them accordingly, then they'll get an appropriate amount of data, so they don't overfill. So that's Crush. That's sort of the magic that figures out where all the data in the systems could go, and everybody can repeat this calculation and figure out where to read or to write data. The challenge then is what should RADOS then do once it knows where the data should go? How does it actually store it? And there are 2 strategies. So all the objects that are stored in a pool have to be durable. We have to make sure they're safe. Those pools are broken up into placement groups. So each individual placement group, some subset of the overall data, has to be durable in some way. And we have 2 strategies for doing that. In the case of replication, we simply stamp out copies of the placement group. So if we imagine this PG has 2 different objects in it, we just have 3 different OSDs. We store a copy of this placement group on each of those OSDs, and each OSD with that placement group has a complete set of copy of all the objects that are in that PG. So this is nice in the case of recovery. If we need to make a new copy of the PG, we can take any existing copy and just read it and make a new copy somewhere else. So that's great. And it's also convenient in that RADOS lets you change the replication factor at any time in the future. So if I want to go from 3 replicas to 5 replicas, I can just flip a switch in the pool, and RADOS will go off and start creating new copies of these PGs and finding new places to store them. And that's all fine. It's really quite straightforward. Erasure coding is a different reliability strategy, and it works very differently in that instead of having identical copies of placement groups, instead we have different shards, different slices, if you will, of the same placement group. So if the placement group logically contains a number of objects, in this example, which is a 4+2 scheme, we would have 4 shards and have the data that's striped over those 4 shards in a way. And then we would have 2 additional shards that have some sort of parity and redundancy information. So this is really what RAID is doing. Erasure coding is sort of a generalization, a more flexible version of what RAID does. And so we'd have these additional components that provide some redundancy so that if I lose either 1 or 2 of these different shards, I can always read the surviving pieces, do some calculation, and rebuild the data. And you'll notice that erasure coding is much more storage efficient. So these first 4 shards have a complete copy of the original data, and then I have 2 additional shards, so I have sort of a 50% storage overhead to provide a level of redundancy that allows me to lose 2 different devices and still have a full copy of my data or be able to rebuild my data. You'll notice that in the 3x replication case, I can also only survive 2 node failures, lose 2 copies, and still have a surviving copy. But the overall storage overhead is 3x. So this is 1 copy of the data, and I have sort of a 200% overhead versus a 50% overhead. So erasure coding is much more space efficient. Unfortunately, it's less efficient when you're doing recovery because, as I mentioned with replication, you can just read any surviving copy and then write it again. That's pretty straightforward. In an erasure coding case, if I lose one of these shards, I have to read all of the surviving shards and do some calculation in order to regenerate that 1 additional shard. So it's significantly more expensive in terms of network bandwidth and storage I/O. But it works well, particularly for data sets where you have large objects that aren't changing very often. And then RADOS, of course, allows you to store lots of different pools in your cluster. And so you can have multiple specialized pools living within the safe cluster that have different storage policies. So you might have a replicated pool, you might have an erasure-coded pool, some of them using hard disks, some of them using SSDs and so on based on those crush policies. Now by default, and in most cases, all of these pools in the system actually will normally just share devices. So each pool is being broken up into placement groups, and then they're all being sort of randomly spread across the OSDs in the system, unless you are specifically specifying a policy that specifies SSDs or hard disks or something like that. But this sort of mapping between the logical pools and the physical storage devices means that you have elastic and scalable provisioning. So a pool can sort of contain either a little bit of data or an effectively infinite amount of data, as long as you can provision enough OSDs in the background to keep up with your storage demand. As you store data, then you can keep expanding the system and you won't run out of space. You don't have to specify what the size of a pool is up front or anything like that. It's totally virtualized and flexible. This approach also gives you sort of the ability to have uniform management of devices. So I just sort of deal with deploying the Ceph software on new hardware nodes and making sure that they're consuming storage. I throw them into the pool, and then Ceph and Crush will handle remapping data onto them and consuming them. So I have sort of a common workflow for managing the hardware resources, regardless of what is consuming that storage. It might be file storage, CEPHFS, or object storage or something else. Those are all users of RADOS, and RADOS is just providing that storage via these logical pools. So another way to think about this is to consider that RADOS is really virtualizing storage, right? We have these virtualized pool storage abstractions that are sort of variably sized and have some policy around like what performance you want out of it and what the internal redundancy scheme is. But from a user's perspective, they're just a bucket full of objects, right? And then RADOS and Crush do some magic to make sure that these things get replicated and erasure coded and distributed. And on the back end, you have all these different underlying storage devices and software daemons that are actually making this all work. But as far as somebody who's consuming the storage, they don't really know or care. So it turns out to be a very, very powerful thing. In particular, because it means that RADOS can be used as a platform for the higher level services that are built on top of it. So RADOS provides this highly available, highly durable storage service. And then on top of that, we can build object service, block service, and file service. So we're going to move on and talk a bit about RADOS Gateway. the component that provides object storage services in the Ceph. So RGW stands for the RADOS gateway. And as you might imagine, it's a gateway that provides S3 and Swift API compatible object storage. So this is an API that's based on REST. It's usually tunneled over HTTP and provides sort of a high-level object storage service. It's the same type of thing that's often combined with a load balancer and actually exposed to the public internet. So much like Amazon's S3 service, you can have an encrypted connection to these gateways, and you can store and retrieve objects. So the data model that RGW provides is a little bit different than what RADOS does. So the S3 API is built around the idea of having users and buckets, collections of objects, and then objects. They're usually largish blobs of data. So there's a whole model around what the structure of the data is and how the permissions work and how users are allowed to access what objects and so on based around ACLs. All of that is implemented and enforced by RADOS Gateway. And in fact, what it's doing on the back end is mapping that into some internal storage that's dumping into RADOS. So one important thing to recognize is that the objects that we're talking about with RGW object storage are S3 objects. That's not the same thing as the RADOS objects I was talking about a few moments ago that are stored in pools in RADOS. RADOS objects are small. They're usually, less than 10 megabytes, and they can store key value data and byte data and so on. They're sort of this low-level object. RGW objects, S3 objects, are usually pretty big. They can be gigabytes up to terabytes, and they have ACLs associated with them, and they live in buckets, which is a totally different abstraction. You could have, millions of buckets, whereas you only have usually a small number of pools in RADOS and so on. So it's a very different use case. And RADOS Gateway is the component in the system that's sort of making that remapping. And in fact, mostly what's happening is that RGW is taking these big S3 style objects, striping them across a lot of smaller RADOS objects, and then doing the authentication and enforcement. So if we look at a little bit of detail about how that might work, you can imagine that we're storing a large video file via an S3 put or post operation into RGW, and that's getting stored into the backend Ceph cluster. So the first thing that's going to happen is we're going to go look at our metadata. RGW is going to look at our metadata about users, what S3 users and buckets are defined in the system, and make sure that this is a valid request, that it's authenticated, and that the bucket we're putting into actually exists, and what the policies are around it, and so on. It's going to go make an update to this bucket index object. So S3 API is defined around the idea of being able to do a sorted lexicographic enumeration of all the objects in a bucket. So we have to take their sort of S3 names and sort them and put them in an index so we can perform that enumeration. So it's going to make an update there saying we're in the process of updating this object. And then it's going to take the data and stripe it across lots and lots of RADOS objects, dump them all in RADOS. And then when it's done, it'll update the index and say, I'm done. Somebody can now read this object. So big picture, we're taking big S3 objects and we're striping them across RADOS objects. And we're doing this translation between the S3 model where you have users and buckets and enforcing that at the gateway. So you can think about this whole picture as being grouped into something called a zone, right? So you have these RADOS pools that have the actual data that you're storing and the metadata about it. And then you have some number of RADOS gateways. You can scale these out horizontally, less than 10 or tens of them, in fact, in parallel, serving up all this object storage. You can take that sort of whole unit and you can call that a logical zone, which isn't useful in and of itself, but is when you start when you consider RADOS Gateway's federation and geo-replication capabilities. So starting with federation, the idea here is that you can have multiple zones that are deployed that are federated together. So each of these zones might live in a completely different Ceph cluster, maybe in different sites and different geographies and different continents. But they're associated in that there's a replication relationship where all of the user and bucket info, which S3 users exist and which S3 buckets exist, is replicated between these two zones. So they have a shared view of what buckets they're serving. But they have different data. So when you have a request to read a bucket from one RADOS gateway, if it's stored locally, it can service that request and read it here. If you request a bucket foo that's actually stored in a different zone bar, then this gateway knows that because it has all the metadata about that bucket. It can send you a redirect that bounces the client over to the appropriate gateway, and so you can read the data from that location instead. So this is really very similar to what Amazon's global S3 service provides, right? So you have a global namespace of buckets and users. When you create a bucket, you create that bucket in a particular region, which is similar to a zone, and you can request, do reads and writes from that bucket anywhere in the world. And as soon as sort of that access touches the Amazon network, it sends you to the right data center, and so you can read and write that particular data. Now, in addition to that federation capability, RADOS Gateway also has a geo-replication capability, which is sort of extending the zone concept to take multiple zones that are replicating the same content. So if you imagine we had two additional zones, zones C1 and C2. Again, these are totally separate zones. They might be in different clusters and different continents even, but we logically group them into a zone group C. And that essentially tells RADOS Gateway that all of the bucket data, all of the content that's stored in these zones should be replicated. And this can be a unidirectional replication relationship where all the writes happen in one zone and they get sent off to the other one, or it can be bidirectional active-active. So you could have a bucket that's stored in both these continents, both these zones, and you can both do reads and writes from either bucket in either location, and those writes are asynchronously propagated to other zones within that same zone group, and with conflicts resolved using some sort of last writer wins type policy. So that can be very powerful. And then if you sort of imagine then that every bucket that's stored in this overall sort of global federated namespace is placed within a zone group. So the bucket either exists on these zones in zone group C, or the bucket's in zone group B, or the bucket lives in zone group A. And regardless of which gateway you touch, you get sort of sent to the right zone. And then the RADOS gateways, for each of these zones, they sort of scale out horizontally. And they are literally the gateway. So all of this replication between zones is actually tunneled via the gateways over, TLS secured channels between them in a scale-out fashion. So these arrows here are really showing the replication relationship, but the actual data path is always going through the RADOS gateways up here, because they are literally the gateways. So that's federation. RGW is a sort of a robust product with lots of other features as well. So first and foremost, we emphasize very strong S3 API compatibility. This is a huge investment for the project community. We have a test suite we built called S3 Tests. That's a functional test suite that evaluates whether we've sort of correctly implemented the S3 API. This test suite is in fact used by lots of other projects and products that are S3 API compatible. And we implement lots of other APIs, mostly focusing on things that are in S3. So there's STS, which is a secure token service, which allows you to sort of, instead of using the native S3 authentication model, you can integrate with external authentication frameworks, things like Kerberos and so on. We support encryption. There's a whole set of APIs in S3 around this and a few different ways you can manage keys and so forth. So we implement several different flavors of that API. There's inline compression, so that if you put an object, it'll get compressed before it gets written back out to RADOS. We support cores, and static website hosting features, which are used by many people. There's a metadata search capability that integrates with Elasticsearch, so you can do queries over metadata about objects that are stored in a bucket. And we've recently added a pub/sub event stream capability, which is useful in particular if you're integrating with a serverless framework like Knative. So you can imagine putting an object into a bucket in RGW and that triggering an event that then induces a serverless function or Lambda to be called somewhere that does some processing on that data. And that stream can also get fed into Kafka or AMQ or some other components as well. RGW also has a number of sort of tiering storage policy related features. So it supports multiple storage classes where those storage classes map to different RADOS pools. So you can imagine that you might have some RADOS pools that are, erasure coded on hard disks and other ones that are replicated on NVMe devices for very high performance. When you put an object, you can specify which storage class that object might get stored in, or you can set policies and buckets so that all the objects in a bucket are either very fast or very slow, something like that. There's also support for a lifecycle management feature. which allows you to have tiering and re-tiering between those storage classes happen automatically on a time basis, so that maybe when an object is 2 weeks old, it gets moved to the slower storage, and maybe when it's 6 months old, it gets deleted automatically, that sort of thing. There's also the ability to create an archive zone sort of within that federated view, where that particular zone stores a full historical copy of all the data that has ever been written. So even after an object has been overwritten or deleted, it preserves all copies of that object for compliance and other backup type use cases. And that's RADOS Gateway, sort of a complete, robust S3 API implementation that's used in many different private cloud and private infrastructure environments on premises, but is also used by several public cloud companies offering public object storage services on the open internet. So, next up is RBD, the RADOS block device, which is the component that provides block storage for Ceph. So RBD stands for RADOS block device. Its purpose is to provide a virtual block device that allows you to store disk images in a Ceph RADOS cluster. And at a high level, really what we're doing is we're basically taking a big virtual disk and we're striping it across a bunch of smaller RADOS objects and dumping them to RADOS. And the purpose of this is usually because you can take the storage and decouple it from the host, from the sort of the compute side that's actually consuming that storage. So if you imagine that it's a virtual machine, for example, if the storage is stored in a RADOS cluster attached to the network, you can disaggregate your compute resources from your storage resources and scale them independently. You can take virtual machines and live migrate them between compute hosts and fail them and move them around or whatever without having to touch the storage. The storage is sort of always available over the network. Really, sort of all the use cases that you can imagine, analogous to the EBS service in Amazon. And RBD is accessible via both virtualization technologies like KVM and also from a raw Linux device, from a raw Linux host. So if you have a virtual machine, it would consume storage via the VirtIO block driver. The librd and librados implementations of the RBD client link directly into KVM and QEMU. They've been sort of very tightly integrated there for many years, so that virtual machine process is talking directly to the storage cluster on the back end. Or conversely, if you have sort of a regular bare metal Linux host, you can also map a virtual RBD disk device using the RBD driver to a dev RBD raw block device in Linux, and then you can put whatever you want on top, usually a file system. So you can consume that storage. And RBD is tightly integrated with lots of different projects. So libvirt handles all the stuff with QEMU. It's widely used in OpenStack. It's also used in Kubernetes and lots of other sort of cloud stack virtualization technologies. So the RBD supports snapshots and clones, which is sort of table stakes these days for any sort of virtual disk device. So a snapshot is a read-only point-in-time copy of the state of the disk image. So for any RBD image in a Ceph cluster, you can create multiple snapshots on that at any point in time, and there's essentially a snapshot view of the state of that image at that point in time. All those snapshots are sort of logically linked to the original image. So if you have an image called foo, you can go enumerate the snapshots for foo, and you can delete them and make copies of them and so forth. A clone is a little bit different. In contrast to being a read-only, it's actually a writable overlay that's created sort of logically layered on top of an existing snapshot. So a typical way that these are used is that you might have an RBD image that's a base operating system image, like a blank, empty install of a particular Linux distribution, for example. Create a snapshot of that, and then every time you create a new virtual machine in your cloud environment, you simply, in order one time, create a writable overlay of that operating system snapshot, and then start making changes on top of it. And then it kicks in all the sort of copy and write behavior to that. So you can sort of instantly start booting up new virtual machines with a full-blown existing OS install image. And because these clones are first-class images, they can themselves be snapshotted, they can be resized, renamed, all the stuff you'd usually do with an RBD image, you can do to the clones, unlike the snapshots, which are sort of read-only immutable copies. But in both cases, for both snapshots and clones, all this is efficient. So creating snapshots and clones is an order one, near instantaneous process. Doesn't involve copying any data, just fiddling with some metadata. And in both cases, we leverage copy on write support in RADOS so that space is only consumed as data is changed. So if you create lots of snapshots but don't modify anything, the snapshots don't consume any space. Same thing with the clones. A clone doesn't occupy any space until you start modifying the data that was in the original snapshot, and only then does it consume storage resources. So RBD lays data out by mapping it onto lots of objects in RADOS. There are two different types of objects. So the first object is an RBD header. This is just a small object that has metadata about the image. So things like what's its name, how big is it, what are the striping parameters, does it have snapshots, what options are set, that sort of thing. And then the actual content of the block device, which you can imagine as a sort of logical array of blocks in this virtual disk, are sort of arbitrarily carved up, striped, and mapped onto RADOS objects, so that each RADOS object is a chunk of the overall block device. By default, these objects are 4 megabytes, but you can configure that to have any sort of striping scheme that you want. And notably, the important thing to remember is that it's a sparsely allocated. So when you create a new RBD image, it creates the header image, but no data objects are created. So it might be a 4 terabyte image, but it consumes almost no space except for this header. It's not until you actually start writing to a location in this block device that it instantiates this object and writes some data into it. And in fact, these objects themselves are also stored in a sparse fashion. So if you write 4K in the middle of a 4 meg object, it still only consumes 4K of storage. And these objects can get dumped in any RADOS pool. So it can be a replicated pool or a erasure coded pool, depending on what your durability and performance requirements are. So RBD also has an alternative mode of writing data. So a write, instead of just going to the particular location of the block device and mapping to the image and writing there, you can instead enable a journaling mode. And the idea there is that all the writes are first appended to this sort of sequence of journal objects. That's growing here and eventually getting trimmed there. After a write is persisted to the journal and stable, then we can go write it also over into its normal location, and then we can trim the journal. So this journal contains recent data writes, and it also contains any metadata changes, things like resizing the image and creating snapshots and so on. Sort of a full record of all the things that are happening to the image, or recent history at least, are contained within the write journal. So in and of itself, this is a particularly useful capability, except in that it enables us to implement this RBD mirroring feature. So RBD mirroring is the ability to asynchronously mirror a RBD image that's stored in one subcluster into a different subcluster and probably a different location and different data setter and so on. And so in that case, you have the first subcluster, which has somebody consuming the image. It's making writes, it's appending to the journal, and then flushing them all to the data pool, like we just described. But then you also have an RBD mirroring daemon, which is essentially just watching all the writes that are happening to this image in the journal and reading them. And then it's applying them to a copy of the image that's stored in a separate cluster, probably in a separate data center. So this gives you an asynchronous copy of the image in a different cluster. So notably, this is a point in time and crash consistent copy. So if this first cluster blows up, even if all the latest writes haven't been modified, what we have in cluster B is a point in time crash consistent view. So it's as if the thing consuming or writing to the storage crashed a little bit sooner because we lost the last few writes. But it's fully consistent in that it's point in time consistent in that sense. It also mirrors not just the data that's stored in the image, but also all the snapshots and other sort of metadata type changes. So this copy in the second cluster is a sort of a complete clone that has all the properties, not just the actual data. And RBD mirroring supports sort of the full life cycle of events that can happen. So you might lose your first cluster and have to fail over to cluster B and start consuming that and updating this image. Cluster A comes back online. You need to resynchronize the images by rolling back any changes here that were lost and copying the new changes in B back over to A and switching the masters back the other direction and so on. So that full life cycle is supported, making this sort of a robust disaster recovery type solution. It can be set up on a per image basis. So some images might be replicated to this cluster, others might not be replicated at all. or it might be replicated to a different cluster and so on. And there's management capabilities for these RBD mirror daemons so that they can scale out horizontally so that regardless of how many of these different RBD images are being replicated, you can ensure you have the processing and bandwidth and so on to actually manage all that replication traffic across to another cluster. So that's RBD mirroring, sort of a complete disaster recovery solution across multiple Ceph clusters for block storage. RBD has a lot of other notable and useful features. So RBD top gives you a real-time view of I/O activity in the system, what images are being written and read to, and how much bandwidth they're using. There's a quota mechanism that's enforced sort of at the time that the devices are provisioned. So it'll prevent you from creating images and then later filling up the cluster by sort of enforcing the total size of the image at provisioning time. There's the ability to restrict different clients via the authentication keys that they use to connect to the cluster, to restrict them to different private namespaces so they can only see their own RBD images and not access others, even though they might be sharing the same underlying RADOS pool. There's a full set of import and export capabilities for backups and getting incremental diffs and migrating data and all that stuff. And there's a trash capability so that when you delete an image, it'll actually get kept around for some period of time before it's automatically purged to help avoid sort of fat finger type situations. And there are lots of ways that you can access RBD storage. So I talked a bit about the Linux kernel client that allows you to sort of map an image to a device in dev RBD with the kernel sort of handling all that network I/O and storage I/O. You can do the same thing using the kernel NBD feature in NBD mode, where it creates an NBD style device, but that essentially does a pass through to a user space implementation of the librd client. That's useful if you're using sort of the latest user space features that aren't yet implemented in the kernel client. There's an iSCSI gateway, so you can create gateways that take RBD images and expose them over the iSCSI protocol. It's based on the LAO stack, and there's a whole set of tools to manage and configure that. And there's, of course, the librd library, which is the user space implementation of the client library that you could directly link with your application. And that's, in fact, what this sort of NBD process is doing, is taking the user space library and just passing the I/O through from the kernel space. So that's RBD. So RBD is used extensively in the OpenStack community and elsewhere. It gives you that virtual block device abstraction that is much more flexible, scalable, and powerful than alternatives like iSCSI. And finally, that brings us to CEPHFS, which is Ceph's distributed file system. So CEPHFS is a distributed network file system. That means that you get files, directories, things like rename, hard links, and so on. It gives you a concurrent shared access to the same file system namespace from multiple clients that are mounting the same file system. CEPHFS is designed to provide a strong level of consistency and coherent caching, which means that if you make changes to a file in the file system from one node, if another client looks at that file, it will immediately see those changes. So it's a fully coherent view of the data through a combination of locks and leases and so forth. It's important to note that the way that CEPHFS is implemented is by separating data and metadata management. So when a client host mounts CEPHFS and you read and write to a file, the client is writing directly to RADOS, directly to the objects that store that file data. So the I/O path is direct to the OSDs, and it's scalable and high throughput and so on because you have lots of different OSDs and you're bouncing data and so on. Metadata access, on the other hand, goes to a new type of daemon called a metadata server. So metadata access is things like creating files, opening files, listing directories. All that sort of namespace coordination is handled by communicating with these metadata services. And this buys us something very important. It means that we can scale metadata and data independently in the system. So if we need more storage capacity, if we need more I/O throughput, then we can expand the size of the RADOS cluster and just deploy more and more OSDs to get more capacity and throughput. On the other hand, if I have more files, if I have lots and lots of small files, for example, or I just have a workload that's making lots of metadata changes, then I can deploy more metadata server daemons and I can scale the metadata capacity of the CEPHFS file system. So that happens by deploying these Ceph metadata servers. This is a new daemon type that sort of complements the sort of the core RADOS daemons. So the Ceph metadata server daemon's job is to manage the file system namespace. Its primary purpose is to store all that file metadata in RADOS objects. So these daemons are stateless. You don't have any direct storage attached on the nodes where these daemons are running. They're actually just storing all their data back into RADOS. So you can deploy these daemons pretty much anywhere. You just want lots of compute resources and memory. Their main job then is to coordinate file access between clients. So they need to make sure that if multiple clients are accessing the same directory or accessing the same file, they have a coherent view. And so they have to manage the consistency of those client caches and make sure that they're cooperating and so on. So it's managing that cache consistency, locks, leases, and so on. They're not part of the data path. When you actually read and write file data, you go directly to the OSDs. And you can deploy any number of them in a file system. So usually you don't need very many of them, but you can have many tens of them deployed in a system for the same file system in order to scale out that metadata if you so need, if it's necessary. And then you usually also have some standby daemons deployed that are just waiting, so that if one of the primary active ones dies, then one of the standbys can take over and continue service without interruption. So as I mentioned, the metadata from CEPHFS or CEPHFS is stored back into RADOS pools. So the client is directing its metadata operations towards the metadata server. All of those modifications to the namespace are getting journaled into a set of objects in the metadata journal. And then once it's stable there, they get written out to all these objects on a per directory basis. So each directory in the namespace has a RADOS object in the metadata pool. That's essentially a map of file names to inode metadata. And then when you actually want to read and write data, you go directly to the data pool. So unlike RBD, you'll notice that for each file system in CEPHFS, there are at least two different pools, one for data and one for metadata, stored in the RADOS cluster. And you can do tricks like put the metadata pool on SSDs so you can goose the performance here and so on. One of the key challenges in making CEPHFS scale is making this metadata scale. And the problem is, how do you take this sort of complicated hierarchical file structure and distribute it across sort of a linear set of store servers? And the way that Ceph does this is using a technique that it pioneered called dynamic subtree partitioning. And the idea basically is that we take the overall file hierarchy and we partition that hierarchy on a subtree basis, and we map subtrees to different metadata servers. But we do that dynamically based on what the current workload is. So if you have 1 billion files in this file tree and you're not actually looking at them, you might not even load them into memory, and they might all sort of be technically owned by a single metadata server. It's not until you actually start accessing data and loading that metadata into the metadata server's memory that it starts consuming resources. And at that point, then the metadata cluster might dynamically take a subtree of it and pass responsibility for that subtree off to a different metadata server, ship that metadata to another metadata server's cache in a coordinated way so that somebody else is responsible for managing all the updates there. So the clients then, as they're traversing the file system, they sort of dynamically explore the file space. They'll learn that this particular part of the namespace is mapped to a different metadata server, so they learn this partition as they go, as they explore the file system namespace. The subtree partition is nice because you can sort of maintain directory locality. So most metadata workloads are limited to a single directory, a small number of directories, which means that any particular workload is usually talking to a single metadata server. So you get things like cache prefetching and sort of some efficiencies associated with that. But you can also arbitrarily scale the system by sort of carving this hierarchy up into smaller and smaller pieces and mapping it out to a larger and larger number of metadata servers. And in fact, if you have a single directory that's very, very hot, for example, or very, very big, CEPHFS can even fragment that directory into lots of little pieces and then take those fragments and map them to different metadata servers so that you get that scalability in the system. So overall, a very flexible approach to managing your metadata. CEPHFS implements a number of other sort of unique user visible features. The first of those is the way it does snapshots. So lots of file systems can do snapshots. In CEPHFS, you can snapshot not just any file system, but any directory within the file system. And when you snapshot a particular directory, it applies not just to that directory, but all subdirectories nested beneath that point in the file tree. This is in contrast to most file systems where you have to snapshot sort of a volume or a sub-volume. That's sort of a predetermined unit of storage or boundary. So snapshots are point-in-time consistent. And in CEPHFS, that's from the perspective of the POSIX API from the actual syscalls at the client side, unlike some NFS-based file servers, which happen sort of at the client-server boundary when things are written back. So the consistency in a CEPHFS snapshot is a little bit stronger than it is in many other systems. But most importantly, these snapshots are very easily used and consumed via the file system. So you can imagine moving into any directory in the file system, and you see some files. There's no snapshots listed there via the hidden.snap directory. If I want to create a snapshot, I simply do a makedir in this hidden magic directory to create the snapshot, and voila, there it is. This is a fast metadata operation. And we have sort of the usual behavior. So if we delete a file, it's gone. You know, we don't see it here, but if I look on the snapshot, it's still part of the snapshot, and I can still read these files from the snapshot using normal POSIX operations. And when I'm done later, if I want to delete the snapshot, I can just do an rmdir operation, and poof, the snapshot is gone. And that's about it. And in the same way that RBD snapshots clones were efficient, CEPHFS snapshots are efficient too. So the creation and deletion is sort of a fixed immediate operation, and snapshots only consume space in the system when you actually overwrite or modify data. Again, by passing coordinating with some features in the RADOS layer to make sure that it's sort of copy and write all the way up and down the stack. The other unique feature in CEPHFS is its support for recursive accounting. And the underlying capability here is that the metadata servers are maintaining recursive statistics across the entire file hierarchy. And these stats cover file and directory counts, the sizes of files and summations of file sizes, and the most recent modification C time on inodes. And these statistics are visible via virtual X adders. So if you mount the file system and you go into some arbitrary directory and you dump the extended attributes on a directory, for example, you'll see some information about that particular directory, how many files and subdirectories are contained within it. And then you also have all these statistics that are recursive stats. So this is the summation of all bytes stored within this directory recursively, not just this directory, but all subdirectories nested beneath it. And this is the most recent modification time of any file nested beneath this point within the hierarchy. And in fact, if you mount the file system with this rbytes mount option, when you do the mount, and then if you do an ls, this recursive bytes value is the value that's reported as the size of a directory, which can be very convenient, right? So you just do an ls-al, and you can immediately see that this directory contains 4.5 megs of data. Most of it's in this directory. You can see not nested in BAS. I can see that my parent directory is 12 gigs, all that stuff. It's actually the same information that you would get out of a DU, but it's sort of immediate and free. Sadly, having these sizes reported here confuses rsync because sometimes they update a little bit asynchronously, and rsync gets confused when the directory sizes change. It thinks that there's some larger change in it. Spits out a warning message. So unfortunately, by default, this option is turned off. Hopefully in the future sometime we can fix rsync so that it doesn't get confused and we can leave them on. And CEPHFS contains a number of other features. So you can create multiple file systems within the same Ceph cluster. And each of those file systems has sort of its own independent separate set of metadata servers. So you can have tenant or use case isolation if that's what you need. CEPHFS supports extended attributes, X adders, of course, file locking, VF lock and functor locks. You can create quotas. Quotas can be set on any directory in the system and can be set either on a file count or on a byte count. You can do subdirectory nested mounts. So you can, for example, have a client that has an access key that's only allowed to mount its a particular subdirectory, like its home directory, for instance, and it's sort of locked out securely from accessing any other files in the system. You can create multiple storage tiers. So I mentioned that every file system has at least one data pool, but you can actually have multiple data pools, and you can set policies on directories so that files created in different subdirectories get mapped to different RADOS pools. So you might have, everything in /home is mapped to sort of a generic lower performance tier of storage that's backed by hard drives, and you might have other directories that have a policy set on them so that they get the files are created backed by a faster RADOS pool with NVMe and replication, for example. And there are also some other features. There's this lazy IO capability, for example, that allows applications to selectively relax some of the strict consistency behaviors in CEPHFS if they sort of know what they're doing. That can be very helpful in having some high-performance computing applications improve their IO throughput. And as with RBD, there are lots of different ways you can access CEPHFS. So of course, there's a Linux kernel client. This is where we focus most of our efforts. Any recent Linux kernel, you can just do mount-g ceph and to access a CEPHFS file system. There's also a fuse implementation that you can use instead. For example, if you have an older kernel, or if you want to take advantage of some newer different feature, for example. And in certain cases, you can also build CEPHFuse on non-Linux hosts to mount CEPHFS from there. You can export CEPHFS via NFS and CIFS via either the Ganesha or Samba projects. These essentially act as gateways. So you have NFS to a gateway that then talks to CEPHFS, the metadata servers and their RADOS OSDs and so on the back end. And those actually work by linking with libCEPHFS, the user space client implementation, dynamically linking that. And if you want to, you can directly link libCEPHFS into your own application if you have some reason to do so as well. So that's CEPHFS, and that sort of completes our overall picture, right? We have RADOS, which provides this highly reliable, highly available storage service. We have Object S3 API service provided by RADOS Gateway. We have virtual disks provided by the RADOS block device, and we have POSIX distributed file access provided by CEPHFS. All of that within a single cluster running on the same storage hardware. So let's shift gears a little bit and talk a bit about how, as a user, you would actually consume Ceph, how you would manage this type of system. So Ceph has an integrated dashboard. This is built into the Ceph Manager daemon. So it comes with every cluster. You just have to sort of turn it on and set your initial user password, decide what port to run it on, and it'll come up. And the dashboard has sort of three basic rules, right? So you can do monitoring. So you can monitor the health of the cluster and have some very basic information about, how much space is used and so on. It also has a whole bunch of metrics built in. So the manager has a module that allows Prometheus to scrape a lot of very low-level metrics from the cluster. So the Ceph manager aggregates all these internal metrics from all the different daemons in the system, provides a single endpoint that Prometheus can scrape. And then the dashboard has a number of Grafana-based dashboards, graphs and so on, that are embedded within the dashboard that pull that data back out of Prometheus. So if you go into the dashboard and you go into the pools and the OSDs and you click on a specific OSD, you can go look at some low-level metrics about the IO latency on the particular device in this large cluster and pull all that information out of Prometheus and have these nice, pretty Grafana graphs too. So it's a very deep level of monitoring and metrics that it's provided by the dashboard. And finally, the dashboard provides a lot of sort of typical storage admin type day 2 tasks. So things like modifying the Ceph configuration, all the documentation and all that stuff to sort of manage the dashboard. You can do provisioning, creating new pools, creating RBD block devices, managing your NFS gateways, all that stuff. A lot of these day 2 operations, provisioning tasks can all be done through the dashboard. Ceph has some other nice management features. So as I sort of mentioned earlier, Ceph monitors the internal status of the cluster and reports sort of an overall health status. It has error and warning states. Every specific alert has sort of a unique ID, a type associated with it, with associated documentation, so you can tell what that particular warning means and what steps you might want to take or could take to mitigate it, and so on. All the configuration management for the cluster is integrated into the system. So all the configuration options are self-documenting. The configuration is stored by the monitors and distributed automatically to all the different daemons in the system. So you don't have to go poking around the system, modifying configuration files or anything. You can all do that all through the CLI or through the GUI. And that includes things like a history and the ability to roll back configuration and so on. Ceph is a software-defined system that consumes block devices for the OSDs. So in principle, you can sort of layer those OSDs on top of anything, whether it's a raw device or LVM or an iSCSI LUN to whatever. I mean, you can create all sorts of convoluted ways that you stack up different software storage layers. But Ceph in particular makes an attempt to map those devices that it's consuming back down through the stack to raw devices. So it'll reach through LVM layers and so on to figure out what the vendor model and serial number of the physical devices that is being consumed, and report that metadata to the cluster so you can tell which daemons are consuming which device and what host they live on and so on. And it goes further too. It also scrapes health device metrics. For example, smart data on a regular basis gets scraped and stored in RADOS. And if you enable it, Ceph can do device life expectancy prediction, right? So it can look at those metrics and tell you if it thinks that a particular hard disk is going to fail within a couple of weeks. And in fact, by default, it'll just raise a warning. But if you choose, you can also configure the system to preemptively evacuate data from devices that it thinks are going to fail to improve the overall reliability of the system. So instead of waiting to go from 3 replicas to 2 replicas, you can sort of create a 4th replica before that device actually fails, and keep your data that much safer. And finally, there is a telemetry feature. So this is the ability for a Ceph cluster to phone home anonymized metrics about the Ceph cluster. What version it is, how big the cluster is, what APIs are being used, what features are enabled, that sort of thing, can get phoned home and sort of a high-level report back to the Ceph developers, which is very helpful for us to find out like what versions of the software are deployed and what people are using and so on. Recently, we've added crash reports to this mix. So Ceph will sort of automatically generate a crash report whenever one of the daemons crashes, either due to a software bug or some other unforeseen event. And those get collected by the Ceph Manager daemon and archived. So you can query any given Ceph cluster and tell when it's crashed and exactly how it crashed, which daemon and what time, all that good stuff. And these crash reports are very lightweight. They just have some metadata like what version of the software is running and what functions we're currently executing when it crashed. There's no identifying information in here. But if you enable the telemetry feature, then these crash reports will also get phoned home to developers, which means that if we look at the deployed population of Ceph clusters and the community, we can tell what versions of the software people are running and what specific bugs they're hitting and in which versions, which can help the developers immensely in prioritizing which bugs to fix and to tell whether things that were happening previously have stopped happening and when they started happening and all that good stuff. So obviously this is opt-in. If you install Ceph, nothing is ever going to get phoned home without your express clear consent. And so the telemetry feature, of course, allows you to show a dump of the data that it would report. So you can look at it, examine it, make sure it's fine to report that type of information. And only if you approve that can you or should you enable it so that it'll get phoned home. But we're very interested in having users enable this feature because the information is very valuable to us. And if they don't want to, we are also very interested in hearing exactly why, because we'd like to find the right balance that sort of maximizes the value, the developers of the information, but also respects sort of the concerns of users, and ideally gets as many people as possible to participate in the program. So there are lots of different ways you can install Ceph. Historically, the way to do that was via a tool called CephDeploy. This is sort of a bare bones CLI tool written in Python that makes it sort of pretty easy to deploy Ceph clusters. It isn't really maintained anymore. In fact, it's mostly but not quite deprecated. Most people these days use one of these other techniques to deploy Ceph. So there's Ceph Ansible, a set of Ansible playbooks that deploy Ceph on bare metal and enable various features. There's the new Rook project, which is an operator for Kubernetes. This is a new CNCF project that runs Ceph inside a Kubernetes cluster and simplifies and automates a lot of the installation and management and provisioning tasks for Ceph. So Rook is very exciting. There's the DeepSea project. This is a salt-based deployment tool that can run Ceph via Salt Stack. And there are a variety of different Puppet modules, projects. I think this OpenStack one is the most commonly used, but there are several out there. So these are sort of the current options. There's also work in progress on sort of integrating the orchestration and installation experience more directly into Ceph. And the idea here is to create an integrated orchestration API that allows Ceph to reach out to the tool that was used to deploy it in order to do things like restart daemons and upgrade and provision new hosts and replace disks and so on, with the goal of providing a unified CLI and GUI experience that's common across all these different tools for all the common day two operations like replacing disks and expanding your cluster and so forth. And the way we would do that was with pluggable integrations with those deployment tools. So a lot of focus on the initial Rook implementation. So the Ceph cluster will actually reach back out to Rook and tell Rook to deploy new OSDs and that sort of thing, Ansible and so on. And in fact, there's also going to be some focus on sort of a bare bones implementation that just does sort of the bare minimum using SSH. So you don't really necessarily need one of these more complicated tools, but have Ceph sort of mostly orchestrating itself, handling the installation and upgrade via containers and so forth. So that's very exciting. Stay tuned for that more in the future. And finally, I'll talk just a little bit about the open source Ceph community and the larger software ecosystem that we exist in. So Ceph is open source software. We have an open development community. Ceph is licensed under the LGPL 2.1 and 3 for the most part. There are little bits and pieces of it that have slightly different licenses, but the bulk of it is LGPL. We do all of our development upstream in the open. We collaborate primarily via GitHub. All our code is reviewed and merged via pull requests on GitHub. We have a bug tracker based on Redmine. There's an email development list where most of the discussion takes place, and we also have an IRC channel where most of the sort of real-time chat takes place as well. We do a lot of meetings over video chat. So we have daily stand-ups for all the different major components, a lot of weekly meetings, a lot of discussion, planning, design meetings, and so on. The full schedule of all those meetings is posted online on the website. And in fact, anybody is welcome to join any of those meetings to either listen in or participate in the conversation. So we invite anybody who's interested to join. And the upstream community, does releases every 9 to 12 months, and we publish ready-to-use packages for a number of different distributions. And of course, we work also very closely with the maintainers and other downstream distributions, so that Ceph is very easy to consume. Over here, we have just a quick snapshot of sort of the top 10 contributors for the last major Ceph release. So you have a mix here of academic institutions, cloud operators and providers, hardware vendors, software vendors, telecom companies, and so on. So very diverse community of people that are contributing and developing Ceph. The Ceph community has also invested a lot of effort over the last decade to integrate with adjacent communities and to make Ceph work very well as a storage platform with other pieces of software. A lot of that effort has gone into the OpenStack platform. So Ceph is very tightly integrated with OpenStack. And in fact, the majority, more than half of all OpenStack installations in the world use Ceph as a storage backend, usually for virtual machines, but also frequently for object storage and file storage as well. More recently, there's a lot of interest and focus on integrating Ceph with Kubernetes as Kubernetes has become the container orchestration platform of choice. That's scale out. You need scale out storage to go with it. Ceph is a natural choice. A lot of that work is via the Rook project, which is a new CNCF project that is an operator for Kubernetes that installs, manages, and provisions Ceph inside a Kubernetes cluster. And of course, there's a lot of work with sort of the underlying communities, with Linux in particular, and with the KVM project to make sure that Ceph works well in those communities and with those software components. There are a number of Ceph events that happen throughout the year. The first is Ceph Days. These are one-day regional events that happen, maybe 10 times a year, spread around the world. Each Ceph Day is usually between 50 and 200 people, depending on the location. Usually it's a single track of technical talks and is sort of mostly user-focused. But these are very popular. They're very cheap. And if they happen in your area, they're very easy to attend. For more information, go look at the webpage. You can find out all about the upcoming Ceph Days, where they're going to be, and if the CFP is open if you want to speak at them as well. We also, every year, have a 2-day global event we call Cephalocon. Usually it's in the spring, and these are larger events, anywhere from 350 to 1,000 people. And the idea here is to have multiple tracks and bring together users, developers, and vendors from around the world into one location once a year to talk about the latest and greatest in the Ceph community. So for more information about Cephalocon, you can go to the website there and find out about past events. All of the talks at all past Cephalocons are all posted on YouTube, so you can also go look at the type of content you see that's been available at those events. I'm pleased to share that there's also a foundation that supports the Ceph project. The foundation is administered in conjunction with the Linux Foundation, whose support we very much appreciate. The foundation is an organization of industry members that support the CEPH project and the CEPH community. So we currently have 35 members. That's a mix of different hardware and software vendors, cloud companies, major users of CEPH, and academic and government institutions that are involved in developing and doing research in CEPH and CEPH adjacent spaces. And the foundation primarily concerns itself with things like planning the sort of global events, helping support and manage the upstream CI infrastructure that supports the project, providing hardware for the community test lab, making sure our documentation is up to date, and generally using its financial resources to do whatever it can to support the CEPH project and the growth of the CEPH user and developer communities. Here's a quick snapshot of the current members of that foundation. Again, these are the premier members that are part of the governing board. Again, you have a full mix of cloud companies, hardware vendors, software vendors, and so on. We also have a number of general members that support the foundation financially, and also nonprofit and academic institutions, government institutions that are members that are supporting the project in non-financial ways. And that's what we have. So for more information, there's a lot of available resources to find out more about CEPH. There's of course the website. You can follow us on Twitter. We have lots of documentation. It's all online and versioned and so forth. A lot of the discussion happens over email. So we have an announcement list. There's a users list with a lot of discussions, asking questions about how to use CEPH, and it's a very, very active community here. And there's also a developer list with all the developers actually building and working on the future versions of CEPH. Both communities also congregate on IRC. All of that's done through GitHub. I also encourage you to check out the CEPH YouTube channel. That's where this talk is going to be posted and past CEPH talks. As I mentioned, all of the past talks at CEPHLOCONs were all recorded and will be recorded and are all posted on YouTube. We also have a lot of our weekly meetings get recorded and posted there, and lots of other good resources. So if you're looking to learn more, definitely encourage you to check out YouTube. And that's it. Thank you very much for listening, and I hope this was helpful, and have a nice day.